Thank you, Professor Abe and Professor Lei, Professor Taniguchi, for giving me such an opportunity. And I thank for all those who support this workshop. And that is great. So today, I'd like to talk to you about an extended sine-skewed structural distribution and its application to a model on a cylinder. This is a joint work with Professor Shiohama and Professor Abe. This is an outline of my presentation. So structural data are recorded as points on the unit circle and arise in biology, geography, medicine, astronomy, and in many other fields. For example, here is a data set of the orientations of termite mounds. This is such a plot. The data set is available in our package Structura. In real structural data, there are not a few distributions that show asymmetric shapes, so still symmetric structural models have been proposed by many authors. So there are some desirable properties in statistical models that we now focus on the following. The first is the ability to fit data of various shapes. The second is the easy of computing likelihood function and some moments. The third is the easy of interpreting parameters. For example, a good parameterization and identifiability. The sine-skewed form Mises and sine-skewed rapid course distributions proposed by Abe and Pusey satisfy the properties 1 through 3. Okay. But the sine-skewed structural distributions are known to be difficult to be largely asymmetric near the modes of the distribution. For a motivated example, here is the data set of the orientations of termite mounds. So we fit the sine-skewed form Mises distribution to the data set. An estimated value for the skewness parameter lambda appears at the boundary of the parameter space because lambda hat has a value 1. So this indicates a stronger symmetry. This indicates that a stronger symmetry is likely needed to describe the data distribution. So in this talk, we apply the still rotationally symmetric distributions given in Lei and Bardeville to extend the sine-skewed structural distributions. We also use the extended sine-skewed structural distribution to propose a new cylindrical distribution. Now, let me briefly review generalized asymmetric distribution on the hypersphere. So, for simplicity, the dimension P is set to be 1. And let psi of a function psi of mu be like this. And this is a symmetric density function where C rho is a normalizing constant. And this is a continuous function that is allowed to have an unknown parameter vector rho. So, this is a still rotationally symmetric distribution on the unit circle. Capital G is a monotone increasing continuous function satisfying this expression, which means that capital G is a distribution function. If lambda equals 0, it leads to the base symmetric density, highlighted in blue. For example, capital G of x is said to be this expression, and h rho of x is said to be this expression. So it leads to the density of sine-skewed Laplace distribution. So now we want to choose function capital G and h rho. So that the resulting model can be skewed more significantly than the sine-skewed circular distribution. And sine and sine moments are given in explicit forms. And it's easy to evaluate the log likelihood function. Let me explain the role of the skewing function. The function capital G corresponding the sine-skewed circular distribution is a distribution function of the uniform distribution on the interval from -1 to 1. When we use a function G with a low slope around 0, then the degree of the skewness isn't strong, even if parameter lambda has a value +1 or -1, which is the value at the boundary of parameter space. So we find the skewing function G having a larger slope around 0 with the support from -1 to 1. Thank you. So we consider the density function on the interval from -1 to 1 like this. M is a specified non-negative value and is referred to as order. Let capital Gm of x be the distribution function of Gm of x. Then we propose the extended sine-skewed circular distribution of order m with density defined by this expression. So the word, the extended sine-skewed, is abbreviated as ESS. And F0 is a symmetric base density, such as the von Mises and the Laplace distributions. Mu is a location parameter, and lambda is a skewness parameter, and the vector rho controls the other shape. The ES circular distribution can be defined for any non-negative value, but it's written with that integral sign when m is a non-negative integer. Actually, for m equals 0, 1, 2, and so on, capital Gm of x is written written as a polynomial function of x. So it's easy to evaluate the log likelihood function. These are examples of the skewing function G. So this figure plots the curves of the extended sine-skewed von Mises distribution with mu being pi divided by 2 and kappa being 8. The left top panel shows the density of order 0. The right top panel shows the density of order 1. And the left bottom panel shows the density of order 5. So we can see from this figure that the higher the order, the higher the asymmetric performance. Now, I'll explain, I'll apply the proposed string function to a cylindrical model. Before I giving the proposed distribution, let me briefly review a tractable cylindrical distribution proposed by Abe and Ray. The distribution, the density is given by this expression. This is a hyperbolic sine and tangent function of kappa. So we use the approach of Abe and Ray to propose a new cylindrical distribution whose marginal distribution of theta is the extended sine-skewed Lambda-Cauchy distribution. Thank you. So we propose a new cylindrical distribution of random variables theta and x with density defined by this expression. Alpha, beta, kappa, mu, and lambda are parameters. We say this distribution a widely extended sine-skewed von Mises distribution. So the marginal density of theta becomes a ESS Lambda-Cauchy distribution with concentration rho given by this expression. And the marginal density of x is given by this function. And the conditional density of theta given x is a ESS von Mises distribution of order n with concentration defined by this expression, which is highlighted in blue. And the conditional density of x given theta becomes a Weibel distribution with shape parameter highlighted in red. This figure shows the contours of the proposed distributions. So as skewness parameter lambda approaches 1, the distribution of theta of the vertical axis gets more skewed. And the order m acts to boost the degree of skewness. Now, let me explain some theoretical properties. Let capital H be a parameter space and let capital Fm be a family of the Weibel extended sine-skewed von Mises distributions. Now, for each m equal to 0, 1, 2, and so on, the family Fm is identifiable. This is proved by using the result of this and this. Next, let me explain the moment expressions. Let this be the associated Legendre function of the first kind of degree in U and order m. Then the moments of x to the power of k times sine theta and x to the power of k times sine s theta are given by these expressions. So, but this moment includes the integral sign. But for each m, this we can we have the explicit expression without the integral sign. The case of order m equal to 2 is given by this expression. The case m greater than or equal to 3 can be also written in closed forms. Next, let me explain real data analysis for the data set of distances and directions by little blue periwinkles. So the very little blue periwinkles are kind of snails. The data set is given in Fisher and Lee. To estimate parameters, we use the maximum likelihood methods. So, thank you. So this is a log likelihood function, and this is a maximum likelihood estimator. So to obtain the estimation, we need to choose the order m. So we consider two methods for selecting order m. The first is the maximum log likelihood approach, which is given by this expression. Capital M is a specified upper bound. The second is to select order m that minimizes Takasaki formation criterion. This term measures how much the model used for estimation deviates from the true model. This table shows the result of estimation. The model with m equal to 0 is a cylindrical distribution proposed by Abe and Ray. So the log likelihood, maximum log likelihood approach picks the model of order 3, and TIC approach picks the model of order 5. The figure shows the contours of the fitting distributions. This is the distribution of order 3, and this is the distribution of order 5. Finally, how many more minutes? 10? Oh, 8? Thank you. There is less time, but okay. Now let me apply the proposed skewing function to a hidden Markov model. The capital AT is a discrete Markov process with k-state space, which isn't observed, and capital A is a matrix of transition probability. Then the random variables theta t and xt are generated from the probability distribution corresponding to the randomly assigned states it. Now, as a component, we use the proposed cylindrical distribution. We apply the proposed distribution to the data set of wind directions and speed measured in Shionomisaki in Japan. So this table shows the result of estimation. So what is just important to notice here is the value of the log likelihood function. This model improves the model proposed by Laguna et al. Finally, we finished my talk by mentioning concluding remarks. The marginal distribution of theta in the proposed cylindrical model is skewed more strongly than the sine-skewed circular distribution. So the estimated value for lambda can be an interior point in the parameter space. But as a note, our proposed distribution isn't always better than the existing distribution. It depends on the shape of distribution, such as the tail. Next, it isn't clear whether the ES rapid cost distribution is unimodal. On the other hand, it's known that the sine-skewed rapid cost distribution is unimodal. Finally, it's challenging to select suitable order M. We hope that the estimated M will approach a certain value as the sample size is increased. But we confirmed through simulation that this isn't the case. Thank you for your attention.